So here in problem 2, what we're dealing with is a reactive process that involves a bioreactor. And in this bioreactor, what we have are cells. And these cells, what they do is they basically consume reactants, and they metabolize these reactants and end up producing or spitting out product molecules. Okay, so you could even think of these cells themselves as little tiny reactors. And so in this problem 2 statement, what we have is a batch reactor that's filled with the biomass of T hypotheticum. And the cells in this biomass, they can't be heated above 42 degrees Celsius, otherwise they die. And in our well-insulated batch fermenter, we contain these cells, and they metabolize ethanol via this reaction, where we have 1 mole of liquid ethanol, which reacts with 3 moles of oxygen gas to form 2 moles of carbon dioxide gas and 3 moles of liquid water. And so during this reaction, when the cells are metabolizing this ethanol, they give off heat. Okay? And so if our reactor is initially charged with 1 mole of ethanol, 3 moles of oxygen gas, and 5 moles of water, liquid water, all at 25 degrees Celsius. If 5% of this ethanol is consumed, so molar percent, the problem asks us, what's the final temperature of the fermenter? And do these cells survive? So basically, does the temperature stay below 42 degrees Celsius? And so what I want you to do now is I want you to pause the video, and I want you to use the information in the problem statement in order to develop a basis and use it to design a process flow diagram. Based on the information in the problem statement, we could develop a process flow diagram that looks like this, where we have a reactor that's full of this T hypotheticum cells, and into the reactor we initially charge 1 mole of the ethanol, 3 moles of the oxygen, and 5 moles of liquid water. For our basis, we're using 1 mole of the ethanol, since the problem statement told us that. All right? After the process, what we take out of the batch fermenter is the reaction produces carbon dioxide and water, but there's also leftover ethanol and oxygen as well. So that's the stuff that did not react. We're also told that the conversion of the ethanol in the reactor is 5%, so F is equal to 0.05. All right? As far as unknowns in our system, so we're told what's initially fed into the system, and we're told that it's at 25 degrees C. But we don't really have any information about what's taken out of the fermenter. Other than that, only 5 mole percent of the ethanol has been reacted. All right? For the reaction that's going on in the system, what we're told is that 1 mole of the ethanol reacts with 3 moles of oxygen gas to form 2 moles of carbon dioxide and 3 moles of liquid water. All right? And so these are all the knowns and unknowns in our system. What I drew here below is the enthalpy table that we're going to be using later. And so you can see here what I labeled are the different species in our system, the amount of moles that are initially there, along with these specific enthalpies, and also the molar amounts of things that are there at the end, along with their specific enthalpies. Okay? Now that we've identified what our knowns and unknowns are, we could do a degree of freedom analysis in order to figure out if we have enough information to solve for all our unknowns. And since we're dealing with reactions, we're going to do a extent of reaction degree of freedom analysis. And so for this degree of freedom analysis, what we need are the number of unknowns, number of independent reactions, number of independent species, and other equations. Okay? And so now what I want you to do is to pause the video and identify the number of each of these 4 different classes. Okay, so the number of unknowns we have in our system is 5, right? Because we basically don't know anything about the product stream. And so we don't know the molar amounts of ethanol, oxygen, carbon dioxide, the water. We also don't know the temperature of our product as well. The number of independent reactions is 1. Number of independent species, it turns out all the species in our system are independent. As far as the other equations we could use, there are 2 of them. We could always use our energy balance, and we could also use that information about the conversion of the ethanol. And so to calculate our degree of freedom, we take the number of unknowns, add on the number of independent reactions, subtract the number of species, and then subtract off any other pieces of information. And this gives us a degree of freedom of 0. And so we should be able to solve for all the pieces of information, or all the unknowns in our problem. Now that we've done the degree of freedom analysis, let's now move on to solving all the material balances for the species in this problem. So let's start with the ethanol material balance. Okay? And so we'll write our general balance equation. And let's start to simplify. And so once again, we're working with a batch system. And so what that means is throughout at least the process, mass does not, or material does not cross our system boundaries. And so that tells us that our input or output streams should be 0. So we'll write here batch. Okay? Now, in our system, we're not producing any ethanol. The reaction only consumes it. So our generation term is going to be 0, and our consumption term is a finite value. Now, since this is a closed system, we also know, or just in general, we also know that the accumulation can also be written in terms of the final and the initial amounts in our system. And so if we rearrange this, what we get is that the initial amount minus the consumption is equal to the final amount of ethanol in the system. So let's identify what each of these terms are. For the initial amount, that's just going to be equal to the amount of ethanol that's in stream 1. So N1 ethanol. For the final amount, that's equal to the amount of ethanol that's in stream 2. For our consumption term, we could write this 2 different ways. Well, first of all, the way we should think about it is that our consumption term is, we could describe it as the amount of ethanol that is reacted in our system. And this amount can be calculated 2 different ways. The first way we could do it is in terms of the yield of the ethanol. And so by definition, the yield is the moles of ethanol that's reacted divided by the moles of ethanol that's fed into the system. And so just by rearranging that equation I just described, what we could say is that the moles that's reacted here, that's going to be equal to the moles of ethanol that's fed into the system times the yield of ethanol, or the conversion. Sorry, not yield. F is conversion. Okay. So now that we have this relationship, we could just plug in, because we know that this is 1 mole, and we know that this conversion is 0.05. And so multiplying that gives us 0.05 moles of ethanol that's reacted. Another way we could define the consumption term or calculate it is in terms of the extent of reaction. And so what we'll do here is we'll say that the moles of ethanol that's reacted is equal to the product of the stoichiometric coefficient of ethanol in the reaction times this extent of reaction. Based on the reaction, we know that this value is minus 1 mole, but we only care about its magnitude. And so by rearranging these relationships, what we could say is that our extent of reaction is equal to the amount of moles of ethanol that's reacted divided by that stoichiometric coefficient. And so that gives us a value of 0.05. Now that we have this extended reaction, which will be useful later, we could go back to the material balance that we derived for ethanol, and we could use it to solve for our last unknown. And so what we have is the final amount of ethanol, which is the N2 ethanol moles, is equal to the amount of ethanol that's fed into or initially in the system minus that consumption. So minus this consumption term, which I'll write in terms of the extended reaction. Okay? The only unknown we have left is this. So if we plug in for the other values, what we get is that the amount of ethanol that's left over is 0.95. And that makes sense because the conversion that we're working with here is fairly low. It's only 5%. Okay, we finish with ethanol. Let's now move on to the oxygen. So the O2 material balance. So we'll start with our general balance equation. We'll simplify. This is a batch. We're not generating any oxygen. We are consuming it. And we know that this is equal to the final minus the initial. Okay. Therefore, once again, our initial minus the consumption is equal to the final amount. All right, so let's fill in for all these values. Okay, and so for the initial amount, this is basically going to be very similar to what we did for the ethanol. So the initial amount is the oxygen that is initially charged into the system. The final amount is the oxygen that's taken out of the system, N2O2. And our consumption term, we could write in terms of the extended reaction. All right, and so in our reaction, we know that this value is -3 moles. And previously, we solved for that extended reaction. And so if we set up our material balance, what we could say is that the final amount of oxygen in the system is just equal to this relationship. Right, and our only unknown left is this. And so if we plug in all the values, the number that we get is 2.85 moles. Okay, let's continue on to carbon dioxide. So CO2 material balance, input minus output plus generation minus consumption. So it's still a batch system, so that's going to be 0. Now, we're looking at the products here, so we are generating carbon dioxide, and we're not consuming any. All right, and we still know that this accumulation is equal to the final amount minus the initial amount. And so what we could say here is that the initial amount, we know in the system we didn't charge it with any carbon dioxide, so this is 0. And so what we're left with is that the generation is equal to the final amount. So let's figure out what each of those terms are. So the final amount, that's the N2 CO2. And our generation term, we could write in terms of the extended reaction, because it's going to be that stoichiometric coefficient times our extended reaction. And based on a reaction, we know this value is positive 2 moles. All right. And so this tells us that N2CO2 is equal to this relationship. The only value we don't know is that. And so if we plug in, we should get that 0.1 moles of CO2 were formed. Okay, and finally, we now get to the water material balance. So A is equal to I minus O plus G minus C. Still a batch. Oh, yeah, it's still a batch. This reaction does produce or generate water. It does not consume. So this is 0. And we know this is equal to the finest minus the initial. We do have water at the end, and we also have water at the beginning, right? 5 moles are fed in. And so if we rearrange this equation, what we get is that the initial plus the generation term gives us our final. We can now fill in what each of these terms is. So the initial is equal to the amount of water that's fed into the system in stream 1. The final is the moles of water in stream 2. And the generation term, that's going to be equal to, in terms of the extended reaction, the molar coefficient of the H2O in our reaction times the extended reaction. And from our reaction, we know that this value is equal to 3 moles, and we care only about the magnitude. And so if we put together this material balance, what we get is that N2H2O is equal to N1H2O plus our extended reaction times the stoichiometric coefficient. All right, and our only unknown is N2H2O. So if we plug in for everything, what we get is 5.15 moles of water is N2H2O. So now that we've solved for all the molar amounts in our problem, what we need to do now is we need to proceed to the energy balance and solve for the enthalpies, and that will help us identify the temperature of our product stream. To start with that, what we're going to do is we're actually going to first calculate the standard enthalpy of reaction for our reaction. Okay? So let's now calculate our standard enthalpy of reaction, our delta HR. And the way we're going to do it here is we're going to do it via the heat of combustion method. Okay? And you'll see why I chose this method in a bit. Okay? In any case, with the heat of combustion method, the way we calculate our standard enthalpy of reaction is it's going to be taken as first the reactants, the sum of the reactants, and taking their stoichiometric coefficients in the reaction times the heat of combustion, or the standard heat of combustion. All right? And what we subtract off is the sum of our products for the same sort of operation. Okay? All right, and so if we expand out these terms to fill in the reaction for our system, what we get is our reactants. So we start with ethanol, and we have the heat combustion of ethanol, the standard one. And now we take the oxygen, and we subtract off all the products. So the CO2 and the water. Okay. All right, and so really the next thing we should do is we should look up what all these heat of combustion terms are. Okay? And so what I want you to do now is I want you to pause the video, and I want you to go to table 1 or table B1 and look up what these enthalpy of combustion values are. Okay, and so you may have noticed some difficulty finding the enthalpy of combustion values for some of the species in this problem. And that's what I wanted to point out, is that the reason I chose the enthalpy of combustion for this problem is we're basically dealing with a reaction that is a combustion reaction, right? We're taking ethanol, we're reacting it with oxygen, and we're producing carbon dioxide and water. And so those are the same, essentially the same species that are involved in a combustion reaction. And I mentioned this in the enthalpy of combustion reaction video, is that if any of your species, when you're doing the enthalpy combustion method, and any of your species in your problem are involved in the enthalpy, are typical combustion reaction products, so CO2, H2O, or O2, if those are involved in your problem or your reaction, you could actually say that their enthalpy of combustions are just equal to 0. And that's by definition. In fact, you probably noticed that when you look up these species in table B1 and look for their enthalpy combustion values, you'll notice that they aren't there. They're just dashes. All right? And that's because you're supposed to just assume that these values are 0. And so this significantly simplifies our standard enthalpy of reaction calculation, because all it is equal to is our ethanol term. Okay? And so I'll write this out here. It's just equal to this. All right? And this you can find in table B1. Okay? And so if you look up the value and you plug in all the numbers, you should find a value of negative 1366.91 kilojoules. Well, I'll just write it in terms of kilojoules. I guess it's kilojoules per mole since we're multiplying it by that. What you end up getting is you're just multiplying it by 1, so you get the same value. Okay? So this is what our enthalpy of reaction is. Standard enthalpy of reaction is for this reaction. I do want to point out that if you chose to do this problem via the heat of formation method, you should get the same exact result if used. And so as an exercise, I encourage you to actually go out and do that calculation. And you'll see that even though the heat of formation values are different for each of these species, when you add up the total sum, you should get negative 1366.91 kilojoules. Same exact number. Now that we have our standard delta HR, we can now proceed to our energy balance. All right, so let's go with black here. Let's now look at the energy balance. Okay, and so we're dealing with a batch system, and so we should start with the general energy balance equation for a batch system. So we have our internal energy plus the kinetic energy term plus the potential energy term is equal to the heat plus the work. Okay? We could assume that the change in kinetic energy and the change in potential energy in our system is 0. And the problem statement also said that this was an insulated batch fermenter. So our heat term is equal to 0. Okay? We have an adiabatic type system. And so what we're left with is that delta U is equal to the work. Okay? But we're dealing with enthalpies of reactions and things like that. So really what we want to do is, in the end, we want to get to a place where we're trying to calculate enthalpies, delta H. All right? And to do that, what we have to remember is what our work term is equal to. Okay? There doesn't seem to be any moving parts in our system, so the shaft work is equal to 0. We don't have any electric work. There's no radiated work. But potentially, or there is what we call mechanical work in our system, right? And that's equal to the difference between the pressure times volume at the beginning of the process minus the pressure times volume at the end of the process, okay? So just in general, right? That's just in general one definition of mechanical work. All right? And when we think about this, or let's look closer at each of these terms in our problem statement. As far as the pressure is concerned, we actually weren't given any information about pressure, right? We don't even know what pressure all this reaction stuff is occurring at. So one thing we could assume, since we don't have any information there, is that this reaction, or this entire process, is probably just occurring at 1 atm, right? And that the pressure likely doesn't change too much. All right? So that's one thing we could assume. But as far as the volume is concerned, our specific or our molar volume of the system is probably going to be changing a lot. And that's because we're dealing with a reaction here, right? So we're turning ethanol and oxygen into carbon dioxide and water. And each of those things has, a distinct molar volume. And so for our system, we likely are, and because the composition is changing over time, our molar volumes are likely changing over the time as well. Those molar volumes are likely changing due to reaction. Okay? In any case, we don't have to worry about the specifics of this work term. I just wanted to, give context for why we're considering it. All right? In any case, so what we have here, we had delta U is equal to W. But what I'm going to do is I'll first just expand it out like this. Initial minus PV final. Right? And then I'm going to move everything to the left-hand side. So what we have is this. PV final minus PV initial. And then I'm going to rewrite it like this. Since we have final minus initial, what we have now is a delta PV. And that, by definition, is delta H. And since we moved everything to the left-hand side, the right-hand side is now 0. Okay? And so now we are dealing with enthalpies. All right? So now that we have, this is our energy balance. All right? And so in order to solve, for our final unknown, which was temperature, we need to expand out our delta H. All right? But before we do that, let's think about what our reference conditions are going to be for the system. Okay? All right? And so, once again, since we're dealing with a reaction, and our standard enthalpy of reaction for our system is defined as, or typically defined for being 25 degrees Celsius and 1 atm, it's best if we just set those temperatures and pressures as the reference temperature and reference pressure for each of our species. Okay? So for ethanol, we start with a liquid, so let's keep that as the phase. So that's at 25 C, 1 atm. The oxygen, we start as a vapor, so we'll set 25 C and 1 atm. All right. Carbon dioxide, it's also a vapor, 25 C, 1 atm. And then the water, that's going to be liquid, 25 C, 1 atm. Okay? And at this point, we could also start filling in our enthalpy table what the molar amounts are, right? Because when we went through the material balances, we solved what each of these terms is. So ethanol, 1 mole, O2, 3 moles. We don't have any carbon dioxide. 5 moles of the water. And as far as the final amounts, we know we have 0.95 moles, 2.85 moles. We have 0.10 moles here, and then 5.15 moles there. Okay, and then for the specific enthalpies, we'll fill those in as we keep going through our delta H calculation. Okay, let's now jump back to our energy balance, and let's expand it out. So we know it's equal to 0, delta H is, but we also know, just in general, it's equal to this equation, where if we account for the standard enthalpy of reaction, we add on to that these enthalpies of all our products, which is just the product of the moles times the molar enthalpy, and then we subtract off the enthalpies of our reactants using the same product. Okay. Let's now expand out these sum terms. So what we have is this. So for all our products, we have N2 of the ethanol times its specific enthalpy, or molar enthalpy, I mean. We have the same for oxygen. We have the same for carbon dioxide. We have the same for water. And then we subtract off everything that was fed into the system. N1 ethanol, N1 oxygen, and then also the water. Okay. And I realize I should probably, just to avoid any confusion, I know I said products and reactants here, but really it's probably better to just say the final minus the initial amounts. Alright. Okay? Alright, the good thing here is, there are a lot of terms in this equation, but what we have to remember is that the ethanol, oxygen, and water that are charged into the system, those are all at 25 degrees Celsius and presumably 1 atm. And so those are, that matches the reference conditions we set for our system. And so these terms we can just say are 0 right here. Right, and so all that's left is we need to figure out what these specific enthalpies are for each of the species in stream 2. Okay? And so what I want you to do now is I want you to pause the video, and I want you to identify how we're going to calculate each of these specific the molar enthalpy values. Let's proceed. Before I plug in for all these specific enthalpy values, I'm just going to rewrite the equation we derived for delta H. So we have the term that accounts for reaction at the standard conditions, and then we have basically just the enthalpies of all the stuff at the end. So the ethanol, here, we have the oxygen, we have the carbon dioxide, and we have the water. Alright. And this entire sum, all of this stuff, that's equal to 0. Okay, and so this is what I'll say is equation 1. And so now we need to figure out what each of these molar enthalpies is. And the way we're going to get them is, we're just going to get them by integrating the heat capacity values that we could find in the back of the book. All right, so I'll go to this next page, and we'll go species by species. So our H2 ethanol here, we could say that its molar enthalpy is just the integral of its heat capacity with respect to temperature. And we're dealing with a liquid here. And we're integrating it from its reference temperature, which was 25 C, to its final temperature, which we don't know. That's what we're trying to figure out, T2. Okay? In any case, if we look it up in the back of the book, we find that its heat capacity for the liquid ethanol, at least, is just one term, and when we integrate it, we get this equation. Okay? And this is going to have units of kilojoule per mole. Let's now go to the oxygen. Its molar enthalpy is going to be the same sort of thing. We're integrating its heat capacity from 25 to T2. But this one has a few more terms in its polynomial. Right? And so we get a bit of a longer equation after we integrate. Okay? 158 e to the negative 5 divided by 2. We got T2 squared minus 25 squared. And then the next term is negative. And what we have is 6.076 e to the negative 9 divided by 3. T2 cubed minus 25 cubed. Right, and then plus this t to the fourth term. Right. So that's the specific enthalpy for oxygen. Now let's move on to carbon dioxide. Still the same sort of thing. You know, there's no phase changes that we have to worry about here. So CO2 vapor. And its heat capacity is also a pretty long polynomial. So let's plug in here. Mm. 4.233 negative 5 2 T2 squared minus 25 squared. You're also subtracting 2.887 e to the negative 8 divided by 3 cubed minus 25 cubed. And then you have your t to the fourth term. Your 7.464 e to the negative 12 divided by 4 times to the fourth minus 25 to the fourth. Okay? And then finally, we have the specific enthalpy of the water. And that's, thankfully, much shorter. So, just to clarify, we're still integrating from 25C to T2 the heat capacity of water, but the liquid version. And when we do that, we get a relatively short equation. That's just linear with temperature. Okay. All right. And so at this point, what you need to do is plug in to equation 1, which we designated on the previous page, and then solve for T2. When you do that, what you get is that T2 is equal to 144 degrees Celsius. So that's our final temperature. All right? And the problem statement also asked us, you know, if the cells live, and that threshold was 42 degrees Celsius. And so what this tells us is that our cells are definitely dead. Okay. Alright, so just from metabolizing this ethanol, the cells release a lot of energy, right? And if you don't do a good job of controlling the energy that's released from this reaction, what ends up happening is you just kill all the cells in your reaction. And so, as far as the engineering goes, this tells us that if we build a bioreactor, we need to have a very good system set up in order to basically keep the reactor cool and find a way to dump all the heat that's being emitted from the reaction.